This is the 45th video in a course on single agent search. And in this video, we're going to look at an idea called contraction hierarchies. And we're going to relate it to some of the ideas that have already been looked at in this course with relationship to ways of reducing the state space or simplifying the state space, and some other ways that we haven't looked at yet either. And so we'll take a look at that. So I'll describe how contraction hierarchies work in a minute. But before I do that, we're going to look at a map here and talk about what's going on. But anyway, we're going to look at contraction hierarchies. This is a technique that was, in its current form, was, although there's been quite a bit of work on them in different contexts, developed by Robert Geisberger in Germany. And so let's take a look. But before, as I said, before we get to that, I want to go back and look at jump point search a little bit. And so if we look at jump point search, what I've done here on this map is I have labeled, for this map, I've labeled all the jump points, which are on the corners of obstacles. And when you look at this, when we're doing search using jump point search, we can think about what happens here. In fact, we can think about a particular jump point. And so in this search, when we're going here, the way I'd use this jump point is that I might be searching down in this direction. I hit the jump point, in which case I'm going to restart the canonical ordering and I'll start looking at states in this direction. So we could think about with this, we could start to think about like, what is the graph if I'm going diagonally here? We'd have something like this. We could start to think about the graph that might be induced on a contraction hierarchy. Or sorry, a graph that might be induced on a jump point search on the jump points. If I'm coming around the corner in this direction, then this is the states that would be led to. And of course, I could continue to make more connections here. But now let's think about going back the other direction. So if I'm going back this way, again, I'm going to have my diagonal edges going down here. So I'd be connecting to this point right there. Now this jump point is actually not a jump point in this direction. So I'd actually continue to that point there. I'd continue to this point here. And we also, again, actually there's some points here, which would be jump points, but not necessarily coming from this direction. Okay, so I can continue to do this process. And sorry, I would have, if we could look here, I could be coming this direction, but this isn't a jump point. When I'm coming this direction, I would just get to the wall. It's only a jump point when I'm coming this way. Okay, but if we think about this though, what we can see here is I could start to fill in a graph of thinking about all the directions that I could come in the map, where I might go, where I might connect through my state space. So coming in this direction, if I'm coming this way, then I would restart my canonical ordering. So let's say from this node, I would restart it and come this way. So I would see angles like this. I would see something like this. And anyway, I would continue here. I would also see, if I have this, we'd also continue up into here. So I could take these jump points, I could start connecting them together, and they would give me, I could get full connectivity between all of them, like anybody that's visible. I could think about, well, if I'm actually coming at this jump point and following a particular direction, what might I get there? And this would give me a graph that represents a lot of the connectivity of the world and actually represents many of the shortest paths. Now, this idea here is not directly, doesn't have to directly come from jump point search, but this also comes from an idea called subgoals. And this is an idea that was put forward by Tonsel Uris, working at USC with Sven Koenig. And so he was looking at this and he did a number of post-processing things that could be done on building a graph like this and trying to use it for pathfinding. But the idea here is that we see that many of the states in the state space that are not these jump points are really not very interesting. They're sort of unimportant for the core pieces of our shortest paths. And this is a little bit related to our highway dimension, because we're actually saying that much of the graph here, and this, if we're thinking about this as a graph, thinking about like our connectivity here to our neighbors, then much of this graph is sort of irrelevant. There is this high-level structure which tells us where our shortest paths are going to go, and that's much more important than sort of all the cells that I have in between here. And so what we have this notion that maybe there's some nodes here that are not important. I could maybe get rid of them. And if I got rid of them, then I would have a much smaller problem that would somehow represent the core of the pathfinding problem that I'm trying to solve. And as I mentioned, subgoals here. So subgoals are an idea that look exactly at this, and then they start to reason about maybe we don't, this fact that maybe we don't need all possible connections here. So they have this idea of reachable or direct H reachable and some other things here. But I'm not going to talk about that today, although that, there's a line of research there which is really interesting that has explored a lot of possibilities of what can be done in that space. But setting that aside, so as I said, a reference to go look up if you're wanting to more details. Contraction hierarchies are sort of the embodiment of this idea that there are big portions of the space that we maybe could get rid of without impacting our distances. And so I'm going to show a couple of examples of where these come from. And I'll talk about a couple of things. Contraction hierarchies actually have been particularly popular in road networks where we have changes in cost. Like maybe I have traffic that comes and goes. So they can work particularly well for that, for like small dynamic changes. Don't have time to talk about this in this course, but again, there's a lot of reading out there. But we could think about maybe a cloud. If this is a city here and this is another city, and maybe there's a highway between these cities. And if you're depending on how you're representing this highway, there can be something like a freeway with maybe you're representing turns in the freeway or other things like this that are going on. And you might find that you've got a bunch of edges here, that have cost 1 and a bunch of nodes. Obviously, there's a node sort of connecting into this cloud on each side. And the idea of a contraction hierarchy is that, I can take this piece right here and I can really take this out of the graph, and I can put something that represents all of these little connections here without having to have all these nodes in here. In the same way that there's a bunch of nodes inside the map here, which aren't particularly important. And the idea here is of a contraction hierarchy is, at least at the first stage here, is we're going to put one edge here. And we see this edge has cost 1, 2, 3, 4, 5. If I put a single edge cost 5 in here, then this is equivalent to all of these nodes in here, individual nodes, which again have the individual costs add up to 5. And as long as my start or goal is not in this region right here, then I can just sort of use this single edge right here of cost 5. I've got a smaller world, and now I can represent the full connectivity. I haven't lost anything in terms of my shortest paths. And so that is the idea of contraction hierarchies. And the general idea is that we're going to choose a node and we're going to do a contraction, which is a contraction operation. It's basically to remove this node from the graph. And then we're going to see what shortest paths have changed by removing this node from the graph. So we're going to think about if there's nodes that the shortest path is no longer preserved, we're going to put new edges in. So if I were to remove all of these 4 nodes from the graph, then this would not preserve the shortest path between these states. So we're going to add a new edge, which is going to preserve those paths. So I'm going to show another example of that, and then we'll look at another example that'll show us actually how we do pathfinding here. But let's just practice this process of doing contractions. Okay. So this is a fairly simple example. What we're going to do here is just have a little piece here where all the edges are going to be cost 2, except one node at the top, which is going to have cost 1. And the idea here is we're going to choose a node to contract. And we can see what happens as we contract a node in the graph. And we'll look at this process. So the first node we're going to choose, in fact, the only node for this example that we're going to contract is this node right here. And the idea is I want to remove this node from the graph and then ask what happens after remove it. Okay, so this is going to give me a transformation. It's like an abstraction of my graph. So I'm going to get an edge cost 1, an edge cost 2, another edge cost 2. And this is going to be the remaining graph after I've done this contraction. And now what I'm going to ask is, in this remaining graph, are the shortest paths between all nodes still preserved? And so I can ask between this node and this node, what was the shortest path in this graph? The shortest path was cost 1, and that path is preserved here, is still cost 1. So that's good. I can look at this node right here. I can ask what the shortest path was. And the shortest path between these two nodes before was not cost 4, but it was actually cost 3. Okay, so this node didn't figure into the shortest path, and so this shortest path is still preserved here. Then I can look at these two nodes, and I can see from these two nodes, the shortest path going around the outside, ignoring this node or looking down here, is 5, but going through this node, there was a path cost 4. And so what I need to do now is I need to add a contraction, an edge here. With my contraction, I need to add a shortcut edge. And the shortcut edge is cost 4 here because this represents the cost of going through this node that was removed from the graph. Okay, so I've added an edge, but that's okay because I've preserved what's going on out here. And I've preserved everything else by removing this node. And then I can continue to look at this. If I look at these two nodes, the shortest path is preserved. These two nodes is preserved going here. And then I look at these two nodes and that path is preserved. And so everything else is preserved. So I've taken this node here that has 1, 2, 3, 4, 5, 6, 7 edges and 5 nodes. And I've gotten into a graph with 4 nodes and only 4 edges. So I've got a smaller graph here. And by contracting this node, I was able to add a shortcut here that preserves shortest paths. Okay. And so that's what the contraction hierarchy process is. And so in some sense, like that's all you need to do contraction hierarchies. But, and so if we think about something like subgoals or jump point search, we could think of them being somewhat equivalent to doing contraction hierarchies, except that maybe they're contracting many, many nodes at the same time. So we could think about like simultaneously contracting everything that isn't a jump point here, but in the subgoal notation, anything that isn't a subgoal, and then we'd just be adding back these edges that represent the shortest paths, and they would be much more sparse than the original graph here that had many, well, we have far fewer nodes, and overall we have far fewer edges in the graph that we have. And the question is, well, how do I actually decide what nodes are important or not? And of course, that's a more complicated thing. There's heuristic methods that have looked at. For instance, we can think about, there could be ad hoc measures. For instance, how many edges would be removed if this node is contracted, or how many edges have already been removed around this node. We could also think about how path lengths change or other things like that. And so there's some heuristic methods that could be used. There's actually some nicer, maybe it's not quite as recent now, but there's been some nicer work that's looked at an understanding of how contractions work on grid networks. And so I think Sabina Sturant published a paper on this a couple of years ago, and that was showing some of the things that could be done to build contractions well on grid graphs. So don't have time to talk about that in this lecture, combining that, at least when I'm looking at my time overall for my class. But I want to show one more example of doing a contraction, and this is taken from some common talks from Robert Geisberger's work. And so I'm going to show this example of something similar to what we've done here, where we've just taken a single edge here and we've contracted that away. And so what I'm going to do is a simple example that is going to have 7 nodes here. And this is going to show us how we can actually get our shortest paths back when we are doing this process. So here we have 7 nodes. Okay, and what we're going to do is we're going to think about contracting them as this picture. All of these have edge cost of 1. And so what's going to happen here? So we're going to think about an order of contraction. So the first thing I'm going to contract here is going to be the first node here. So I'm going to draw this in blue. So we're going to do this. This is node number 1. And when I contract this node away, if I look at what happens to my graph down here, for the remaining graph, actually nothing happens. The shortest paths are still the shortest paths. And now we're going to continue this process. And what we're going to do is I'm going to contract this node right here. So we're going to call that node number 2. And we're going to put this just a little bit higher in this hierarchy. So this is where we're going to get the term of contraction hierarchies from. So 2 is being contracted up here. And practically speaking, down at the bottom down here, we've had to add the shortcut edge in between the neighbors on either side of the node, which is cost 2. But we'll see how those are added in as we continue this contraction process. Okay. So the next thing I'm going to do is I'm going to move over here and contract node number 3. And again, what I'd be doing is wanting to add a shortcut edge here. The next step that we're going to do is contract node number 4, which is coming over here. So we've just gone across this path and done this. Node number 4 doesn't introduce any shortcut edges. And at this point, basically 1, 2, 3, 4 have been removed from the map. And what we're going to get next is node 5. And then we'll do node 6 on this side. And then node 7 over here. And what I'm going to do now is I'm going to draw what are the edges that exist. So 1 has an edge cost 1. And because 1 is numbered before 5, so 1 is lower number than 5. And there's an edge cost 1 there. 2 has an edge, sorry, and that's not a directed edge, so let me go back and draw that. I drew it as an arrow because it's going upward, but we'll take care of that in another way. Okay, so now we're going to go from 2 to 5, and there is an edge here that does exist, as there is an edge from 2 to 7 up here. But when we remove 2 from this graph, when we remove 2 from this graph here, what we did is we put this shortcut edge in. So I'm going to go ahead and draw that shortcut edge here. And that shortcut edge has cost 2, whereas the other edges here had cost 1. And if we look at what's going on the other side, we'll see the same thing. We have edges cost 1 here, and we have an edge cost 1 here. And then we see that a shortcut edge was added. So I didn't say this, but when we contract away node number 5, at one point we had 5, 6, and 7. And when we contracted away 5, it didn't impact. This was the only graph that we had right here. It didn't impact the shortest path, so we just removed 5, removed 6. And we didn't need to add shortcut edges there as a result. And so here we're going to get an edge cost 2. And that's going to connect these nodes together. So now what we're going to have this question is, if you started here and sort of said, well, I want the shortest path between 2 nodes, but maybe my nodes aren't actually, like in the same way here, if I said, well, what's the shortest path between this node and this node, what I would have to do is I would have to, and this is what's done in subgoals, is you'd have to connect this node over to the nearest jump points, and you have to connect this node to the nearest jump points, and then you'd be able to do shortest paths between these jump points to figure out actually how to connect them, which in many ways is again also like the waypoints. Sorry, I'm getting the name wrong here, that we looked at in the last lecture. The transit points is what I wanted there. So this would be some, I mean, these would in some ways interact like transit points on this map. But anyway, so getting back to what's going on here, if I'm wanting to do this though, it ends up the contraction hierarchies gives me a good way to do connections. And so the question is, how would I search and find a path from 1 to 4? And the idea here is that if I'm searching from 1, basically we can search in a bidirectional manner, and we can actually only go upward. In fact, we should only go upward here, because as we contract nodes away, then in the remaining graph, shortest paths are preserved. So we can go basically here, and I'll use my highlighter to show this process. As I'm searching from 1 and looking for a shortest path, I'm going to go upwards to 5. And as I'm going from 4, then there's only one choice. I can only go upwards to 6. And when I'm at 5, I could have a choice that I either could go down to 2 or I could go up to 7, but we don't allow these sort of downward connections because 2 is contracted away. The shortest paths that involve 2 have all been replaced by these shortcut edges here. And so we're actually able just to continue this search. So at 5, we're only allowed to go up. So just to be clear, 2 could go upward both to 5 and to 7, but 5 can only go upward towards 7. In the same way over here, 3 could go upward to 6 and upward to 7, but 6 is only allowed to go upward to 7. And at this point, our actually bidirectional searches have met here. And now we actually know that we have the shortest path. So this is a little bit different of a kind of bidirectional search. However, we could actually have many nodes that we decided not to contract. And so there could be many nodes at basically priority 7 at the top. And then we'd have to connect them together in the core piece of the graph that was left there. And what we see here is that this path is cost 1, 2, 3, 4, 5, 6. And that actually represents the shortest path here. But we've been able to get rid of, because we've contracted away some of the nodes here, we didn't actually have to search through these. And so this process of getting the shortest path was much faster than if we had to search the entire graph. Okay, so we see here there's many similarities into the ideas that we've been talking about trying to get rid of parts of this graph. And so, for instance, swamps that we talked about a few videos ago, we could think of these as swamps in some sense. Now, they're not swamps here because they're actually part of the shortest path, but swamps would be area of the graph. Like this is a swamp here. It's an area graph that no shortest path goes to. This is a swamp, and we only need to go here if we're thinking about pathfinding into or out of that area of the graph. So this is very much like a swamp. This is very much like a swamp. We only go out of it. We never go back into it. And so we can see here, again, some similarity in the ideas that have been developed. Now, what happens here is I actually have the length of the shortest path, but I don't have the shortest path itself, because I would say between 5 to 7, I only have the shortcut edge. I don't have the actual edge. And so I would have to encode basically this graph in a way where I'd say, well, this graph unpacks to going through node 2 here. And then I would know that, okay, I can put node 2 in. I can connect these pieces in from node 2. Now, some of these could be shortcut edges, and you could continually do this unpacking process. Something that's very interesting here that we get from contraction hierarchies is so we get the shortest path query very fast, and then I can incrementally give you the path. And we'll see when we talk about the work that's done in games. In games is very much the case that we don't always need to actually get our full paths. We can unpack them sort of one piece at a time. And so that's a speed up that you can get in practice when you're in a real-time environment. You know, if I'm a user asking for a path and then I change my mind, of course, we could think about a much longer path here, but until I can change my mind and say, well, I don't need to worry about unpacking this part of the path. Let's walk along here, which might take a minute, or some portion of that path before I think about unpacking the rest of it, and maybe I'll save that time if the user changes their mind or somebody gets in my way or something else happens when I'm actually doing some sort of pathfinding request. So maybe that's less likely in a GPS environment, but in games we might think about something like this. So contraction hierarchy basically is this idea, this is the hierarchy piece of it, is we get a hierarchy out of the order in which I do the contraction. And we're able to search in this hierarchy by looking from both directions until we get to, sort of doing this contraction in both directions until we get to these most important nodes up here that haven't been contracted. And so, so this is a nice idea. It's a generalization of many of these techniques that that we've used, and it's allowed us to come up with sort of a very principled way of thinking about, hey, I'm removing a node from my graph, but I'm preserving shortest distances. So in this smaller graph, I do this. And so there's this big overlap in what's going on with ideas like jump point search, that they are also saying that there's nodes that I can remove from my graph. And like here, sort of all these nodes don't really matter unless they are the goal. And so that's exactly what subgoals are doing here, is this idea of removing states. So it's a transformation of my state space that is removing nodes that I have to consider for my search. And so this is a great idea. It's used very broadly in road networks. And we can see many of the existing techniques as generalizations or special cases of doing contractions, where we're removing nodes and guarantee that we preserve these distances. So that's all the detail. I'm going to talk about this here, and we're going to look at some other ways of compressing the all-pair shortest path distances in the next video.